Fluorescence quenching. In certain instances, when an excited molecule collides with a normal molecule, even before it undergoes the fluorescence process, the fluorescence may be quenched. That is, during this process, the energy of the excited molecule gets transferred to the molecule with which it collides. So this process is called fluorescence quenching. So there are two types of quenching mechanism. The first one is the internal quenching and the second is the external quenching. Internal quenching occurs within the molecule. That is, when a molecule changes from a singlet excited state to a triplet excited state, and this phenomenon is called internal quenching. Whereas in external quenching, an external substance is involved in this quenching mechanism. So here the quenching may also occurs from an addition of an external substance which absorbs energy from the excited molecule, and this phenomenon is called the external quenching. Again, this external quenching generally occurs by the following two mechanisms. First is a charge transfer mechanism and second is the energy transfer mechanism. So in charge transfer mechanism, it may happen in two ways. In the first way, it is caused by the interaction of the excited and a ground state of similar molecules, that is same type of molecules. First molecule will be in the excited state, whereas the second molecule of the same type will be in the ground state, and these two molecules, when they collide, they form an excimer, so which is represented as A star. So this is the first method. Again, when two dissimilar molecules quench, when two dissimilar molecules also come in contact in a similar way, it forms a mechanism like this, that is A star plus Q giving AQ star. Here the A star will be converted from the singlet state to a triplet state, that is A3, and the energy of this A star will be transferred to Q, which is the quenching molecule, the quencher. So an association between two different molecules of this type, this is called exciplexes. So by these two ways, charge transfer mechanism or external quenching can occur. In the second type of external quenching, that is the energy transfer mechanism, here also two mechanisms have been proposed. First is the Foster mechanism and second is the Dexter mechanism. In the Foster mechanism, here we take the concept of HOMO and LUMO to explain this mechanism. So we need two molecules. First is a donor molecule and second is an acceptor molecule. So donor molecule is the one which absorbs a photon and gets converted to the excited state, and the acceptor molecule accepts this energy from the donor, and while the donor get transferred to the ground state, the acceptor molecule accepts this excess energy from the donor and gets converted to the excited state. So this is a general mechanism. So here we need two molecules, a donor and acceptor, and we need to consider the HOMO and LUMO of both the donor and the acceptor. So in the energy transfer mechanism, in the Foster mechanism, this is how we explain, that is the band gap between the donor, band gap means the difference between the HOMO and the LUMO of the donor molecule, it is greater than the band gap of the acceptor molecule. So in the Foster mechanism, it is possible that when an electron from the LUMO is being transferred to the HOMO, that is the de-excited state, this excess energy is being transferred to the acceptor. So this is the Foster mechanism. Here we can see the resultant spin changes. Here the donor will finally get converted to this paired spin state, whereas acceptor absorbs this energy. That is a kind of a resonance transfer of energy will occur between the donor and the acceptor. As a result, a single electron will get excited from the ground state of the acceptor to the excited state. So this is a kind of transition dipole interaction, and this is a Foster mechanism. Whereas in a Dexter mechanism, it is considered that an electron from the LUMO of the donor is transferred to the LUMO of the acceptor. At the same time, an electron from the HOMO of the acceptor will be transferred to the HOMO of the donor. So this is a simultaneous electron transfer occurring in this Dexter mechanism, and it is also proposed that this type of electron transfer is possible only if there is considerable orbital overlap between the donor and the acceptor molecule. So this is the Dexter mechanism. Whereas in the Foster mechanism, the probability of energy transfer in this case is proportional to the overlap between the emission spectrum of the donor and the absorption spectrum of the acceptor, and decreases with the donor acceptor distance, like 1 by r raised to 6. So this is the difference between the external quenching mechanisms, two types of external quenching mechanisms. Again, we learned about the photochemical yield and different types of processes, that is the primary processes and secondary processes, and we also learned about quantum efficiency. So quantum efficiency phi is equal to the number of molecules reacted divided by the number of photons absorbed, or else another formula is the amount of the substance reacted divided by the amount of photons absorbed. Usually the quantum yield is phi is equal to 1 according to the Stark-Einstein's law of photochemical equivalence, but in real cases the quantum yield can be high or low, and there are different causes for high and low quantum yield. Causes for high quantum yield have been discussed previously, and we'll just continue with the cause of low quantum yield. So in order to be a quantum yield to be lower than 1, there are many possibilities. First is the deactivation of reactive molecule. That is, a molecule when it first absorbs a photon and gets activated, that is when it is converted to the A star state, it is possible that this activation energy of this molecule is lost in many ways. It may either collide with any other ground state molecule and in similar to a quenching mechanism, and it gets deactivated. So there are so many possibilities. So in processes like this, the ultimate result is that a photon, even though a photon is absorbed by a molecule, this molecule is not being transferred to the product state. Instead, it gets deactivated in between, or either through the fluorescence process. So this is the deactivation of reacting molecule. In this case also, the quantum yield can be lower than 1. And second is occurrence of reverse of primary reaction. That is, in case like this, that is 2A molecule is converted to A2 molecule, and in this case the reaction is reversible. That is, this A2 molecule can get back to 2A4. So this is a reverse of a primary reaction. In this case also, the quantum yield will be lesser than 1. Then the third condition is recombination of dissociated fragments. Suppose in a reaction like this, AB absorbing a photon and gets homolytically fission to A and B. And the next step, this A and B again recombines to form AB back. So in this case also the quantum yield will be lesser than 1. There are so many examples of low quantum yield. The first is the dimerization of anthracene. This anthracene molecule also, when this molecule is dissolved in benzene and the solution is exposed to UV light, anthracene will dimerize to form dianthracene. After a few while, this will again get converted back to anthracene. So in this case, the quantum yield is observed to be lower than 1. Another example is the combination of H2 and Br2 to form HBr. So here in this case the primary reaction is in the first step, that is the bromine molecule absorbing a photon forming 2 Br dot, and again this Br dot is reacting with the hydrogen molecule and HBr is formed. In addition to that, an H dot is also formed. These two are the primary reaction process, and the step 2 is a very slow reaction. But in the secondary reactions, the products formed in the primary reactions again react with molecules like Br2 and HBr. These are the secondary reactions. So the products formed during the primary reactions are Br dot and H dot. So these Br dot and H dot again reacts with bromine in this way, that is H dot react with bromine molecule forming HBr and Br dot. Again H dot reacts with another HBr molecule formed during this primary reaction, and the product is H2 molecule and Br dot. So we can see that this H2 is formed back here. Also two Br dot free radicals can combine to form bromine back. So in the secondary reaction steps like this bromine and H2 are formed back. So in such cases also the quantum yield will be decreased. So these are the problems. You have to work out these problems by yourself, and we'll come to the next section. There is cis-trans isomerization of malic acid to fumaric acid. So how is this possible? We know the chemical structure of malic acid. Malic acid, the two carbox groups are in the same side, and these carbons are connected by a pi bond. So when this malic acid is irradiated, the pi bond is easily broken. So here two C dots are formed at these positions. But we know that the free rotation of a carbon-carbon single bond is easily possible. So as a result, this cis configuration can be converted to the trans configuration easily, and we get a structure like this, and the pi bond is reformed. So ultimately we can see that malic acid is being converted to fumaric acid on UV radiation. So this is the cis-trans isomerization process of malic acid to fumaric acid. So the reverse step is also possible, that is fumaric acid can also be converted to malic acid in a similar way. So the lowest excited state of malic acid results from excitation of a pi electron into an anti-bonding pi star orbital. So in this state, the bonding effect of pi orbital is cancelled by anti-bonding effect of pi star orbital, and the resulting carbon-carbon single bond is effectively a single bond. So consequently free rotation around carbon-carbon bond becomes possible. So this is the cis-trans isomerization process. Then you have this photosensitization reactions, and this we have previously discussed in the class, but we are again discussing it here. A photosensitizer is a molecule which can easily absorb a photon, and this energy absorbed by the photosensitizer is being transferred to another molecule. So this is the role of photosensitizer. In many cases, reacting molecules cannot directly interact with this photon or energy. So what happens is that the presence of a photosensitizer molecule or a foreign substance can make the reaction easily possible. So this foreign substance is known as a photosensitizer. So and this molecule is also known as a donor. It absorbs the UV light and it is converted to a singlet excited state. So this is represented as capital D for donor. It a photosensitizer molecule. It absorbs a photon and gets converted to a singlet excited state. So the singlet excited state is then converted to a triplet state, that is D3 state. This is a triplet state of the donor molecule. And this triplet state again, it will transfer its energy to a reacting molecule, that is A. This A, it cannot interact by its own with a photon. So with the help of a photosensitizer like this, A is being able to get converted to the excited state. That is what is happening here. So a D3 molecule, that is a donor molecule in the triplet excited state, it gets reacts with a ground state A molecule. As a result, the energy of this D3 molecule is transferred to A. So D3 molecule will be converted to the ground state D and A will be converted to the excited state, triplet state A3. So now this A3 molecule can easily get converted into the product. So this is the role of a photosensitizer. So let us see an example here. Here this is a most common example, that is a molecule like this, that is the dibenzophenone, and this molecule can actually act as a photosensitizer. So in this case, this molecule is in the ground state. You can see the spin here, S0 paired spin state. It is representing the ground state, and this ground state molecule, at this ground state, this dibenzophenone can absorb a photon and gets converted to a singlet excited state. And again we have a star here, it represents a singlet excited state. This singlet excited state gets converted to the triplet state, that is T1 state. And this T1 state, the molecule is transferring its energy to an acceptor molecule like anthracene. So here the anthracene cannot directly absorb this photon. So this dibenzophenone is helping this anthracene to absorb this photon. So what happens as a result? Energy transfer occurs. So the triplet state dibenzophenone is converted to the singlet state, whereas the anthracene molecule gets converted to the excited state. And this anthracene molecule can then undergo phosphorescence to reach the ground state. So this is the mechanism of photosensitization of anthracene using dibenzophenone. So there are also other examples of photosensitization reaction between hydrogen and oxygen. Here mercury is used as a photosensitizer. Mercury absorbs a photon, gets converted to the excited state. Then this excited state mercury atom, it transfers its energy to hydrogen molecule, and hydrogen free radicals are formed, and then Hg star will get converted to ground state Hg after this energy transfer. And again this H dot formed during this energy transfer step, it will collide with an oxygen molecule and HO2 is formed. Then two molecules like this HO2, two molecules will react to give H2O2, that is hydrogen peroxide and oxygen. This is the reaction step. And similarly a reaction between hydrogen and carbon monoxide to form this HCHO is also facilitated with the help of mercury sensitizer. Other examples are photosynthesis. Here in the case of photosynthesis, chlorophyll molecule is acting as a photosensitizer. It absorbs a photon, gets converted to excited state, and this energy is transferred to carbon dioxide and water for the production of carbohydrate. Then another example is photography. Here also photographic film has a coating of an emulsion consisting of colloidal suspension of silver bromide and photosensitizers in gelatin. So when this is exposed to light, no observable change occurs, but when the exposed plate is immersed in a dilute pyrogallic acid solution, the exposed parts react with it. So this is how silver grains are formed on the plate, and the unreacted silver bromide is removed by dissolving it in a hypo solution to get negative of the film. So this is also a photosensitizer, an example for a photosensitized reaction. Another example is of course the isomerization of cis 2 butene to trans 2 butene. So for this process sulfur dioxide is used. So sulfur dioxide is used as a photosensitizer. It absorbs a photon and gets converted to SO2 star in the excited state, and this SO2 star will transfer its energy to cis 2 butene, and cis 2 butene gets converted to the excited state. The pi bond will be breaking, and then carbon-carbon single bond rotation will become easily possible to get converted to the trans 2 butene, and the trans 2 butene will be converted to the ground state. So these are the examples for photosensitized reactions. Then you have chemiluminescence. So chemiluminescence, it is actually a generation of electromagnetic radiation as light by the release of energy from a chemical reaction. So because of a chemical reaction, luminescence is produced, that is chemiluminescence. So it is actually the reverse of a photochemical reaction. So actually in a photochemical reaction, a photon is absorbed, and with the energy of this photon, chemical reaction is facilitated. Whereas in a chemiluminescence process, chemical reaction first occurs, and as a result the photons are produced. So electromagnetic energy is released. So common examples are the cold light emission by many chemiluminescent reactions, like all these are examples of chemiluminescent reaction. Let us see these. That is the reaction using synthetic compounds and usually involving a highly oxidized species such as peroxide are commonly termed chemiluminescent reaction. Then light emitting reactions arising from a living organism such as firefly or jellyfish are commonly termed bioluminescent reaction, because in these biological organisms are involved. And then light emitting reactions which take place by the use of electrical current are designated as electrochemiluminescent reactions. Then the common examples are like oxidation of either solution of magnesium para-bromophenyl bromide gives rise to chemiluminescence, that is a greenish yellow glow is produced. Again phosphorus and its oxide, it is when it is oxidized, light is emitted, that is glow of phosphorus and its oxide is also an example for chemiluminescence. Then another example is pyrogallol is oxidized by hydrogen peroxide, chemiluminescence will be produced. Then the glow of fireflies is also due to chemiluminescence of a protein luciferin, and oxidation by the presence of an enzyme luciferase. So these are all common examples for chemiluminescence. You can see bioluminescence here. Bioluminescence in the sense because of the action of this luciferin and the enzyme luciferase, because of luciferase is a protein, and because of these action of these substances in biological organisms, luminescence will be produced. So common examples are found in patterns like flashes, that is fireflies, squids, all these organisms, and continuous glow in bacteria and certain fungi. Even certain mushrooms will produce this luminescence. All these are examples for bioluminescence. So this is the end of this unit. can read this text, and if you have any doubts, please contact me.